This video is part 2 to the first video where I go through all the outcomes in Chemistry 30 organic unit. In this video, I'm going to go through all the 2019 and 2017 released items from Alberta Ed, going through both the answers and test-taking strategies of how to deal with diploma-style Alberta questions. I'm going to start with the first general outcome. So I've split up the questions from the order that they were in the 2019 and 2017 items. So we'll go through the first general outcome is all of the drawing, naming, and some of the properties. And then we'll take a look at the more reaction-focused released items second. So the first question goes back to this very first outcome of what is deemed to be organic within the carbon world. So which of the following groups of compounds contain only organic compounds? So we do want the organic ones. We always have to pay attention for whether it's not or is. So some of the things that contain carbon that aren't deemed to be organic are things that contain carbonate. So they can have any positive ion with them. Cyanide, carbon plus a metal, and then the oxides. And then every now and then they'll throw in something tricky, not tricky, but something like cobalt that doesn't even contain carbon, just has a C in it. So as we go through the first one, we're not seeing any of the carbonate, cyanides, metals. So all of these are looking okay. That's an ester, organic halide. So A is looking good. B has a carbon with a metal. So that is not deemed to be organic. Our third one, we've got that cyanide, so that eliminates this sequence as being organic. And the last one, we've got an oxide. So the correct answer is going to be A. Second question that I've picked out. So we always want to read the question first. We have this graphic and box at the top, but try to ignore this and jump down to the question and then come back, particularly when they're very cluttered and noisy boxes. So what is the parent chain? Okay, your teacher might have used parent or stem, both mean the same thing, of the molecule represented above. So we just need the longest chain. So these questions typically are trying to test students to see if they just go right to left or whether they can actually find the longest. We've got this upper chain here, which is going to be part of the longest. We go down, and then if we go up, there's one, over one, and down there's two. So we've got to go down. So the longest sequence is as I've snaked out. And with my students, I always snake out the longest chain, and then I box the side groups. Now we don't need to box the side groups here, but it does help them stick out. So how many carbons do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is non. Next question. Again, we've got a box at the top. Avoid reading the box. Jump right down to the question and then come up and see if you even need to read the box. You don't always need to read the words. So we have a herbicide. It can be classified as something. So let's read the answers. It's either aliphatic or aromatic. So if it's aromatic, it's got one of these benzene rings in it, which there's a few ways to denote them. And we do see one of those benzene rings. So this is aromatic. Okay? So we've narrowed it down to C and D, and we haven't even read the second part. Organic compound with what functional group? So as we scan, we've got some halogens. We've got an O here going to carbons. Now, one strategy I like to do in line structures is circle where line segments meet. Those are always carbons, and on both sides of this O, we just have carbons. Now, this is a functional group we don't study. This is an ether. So nothing that we can do there. And at the end, we have one of those carboxyl groups, C. So there's a C where I'm circling there, C double bond O, OH. What this question is kind of trying to trick or test, see how thorough your knowledge is do you see this? And then think there's something going on with an ester or something with this O being close to it. And then that's not what's going on. So we don't have an ester. That O is too far away. We've got that. So the answer is D. So you never really had to read any of this wording here. None of that helped us. I have done item writing, and one annoying thing is you always have to have a little blurb of why the chemical is relevant to the everyday world, but it's often totally irrelevant to the test taker. So just always be expecting this sort of irrelevant, extra wordy stuff. It's just a mandatory part of writing questions with Alberta Ed. Next question, we've got a matching. There's an outcome that you have to connect organic compounds to everyday chemicals, and it's hard to know all the connections, but you don't have to know them all. In this question, again, skip the box, match to. So we don't have to match everything of the organic compounds to possible uses. So hopefully you would be able to match at least a couple of these. So octane, that's right on a gas pumps, or you have sort of all those numbers on gas pumps relate to how much straight octane there is. So that's a fuel. So 1,5 would be a possible combination. Methane is what heats our homes via our furnaces for most of us. Methanol is one of the things that can be an antifreeze. And ethanoic acid, which is basically vinegar, is what you'd more commonly refer to it as, can be used as a food preservative amongst many other things. You just have to identify two of those possible connections. So there's a lot of possible answers for this question. Next, there's a lot of questions in the released items with that relates to isomers and generic formulas. So we have a C8H16, and you really need to, it's not an outcome to know generic formulas, but they help you answer a lot of questions. So we're given a C8H16, so the pattern here is CnH16 is double 8. So I'd refer this as a 2N. Okay? So that pattern can only occur, never with anes. It just doesn't have enough hydrogen to saturate everything. It can happen in enes and cycloanes. So we know the answer has to fit in one of those two red color-coded categories that I put the blue arrows. So let's see which one of these combinations both work. I'm going to switch to greens where I can circle carbons so that we've got an aromatic ring. All these intersections are carbons. You probably just hopefully know that there's 6 carbons in a ring and 7, 8. So we do have our 8 carbons, but we don't have enough hydrogen in this example. I'm just going to put a little mark where all the H's are. So all these intersections, pick a different color, have just one hydrogen. And then we've got the hydrogen count clearly shown up above. So we don't get to 16. So this one doesn't work. I'm not even going to look at that name. Next one, we've got the right amount of hydrogen, or carbon, sorry. There's 1, 2, 3, 4, 5, 6, 7, 8. And then to count the hydrogens, I'll just put dots again. There's no need writing in all the hydrogen. So this is not an aromatic ring. It's just a cyclohexane. So every time we have 2 lines coming out, there is 2 more H's there. So all of these have 2 H's, all these corners. Now this one has 3 lines coming out of it, so there's only 1 H connected there. So you have 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16. So that works. And does this name work? Yeah. Cyclohexane, that all works. So that's our correct answer. Down here, they've put the cyclo in the wrong place. This should be in front, or the prop. Anyway, there's a couple ways you could look at this being wrong. Either this should be a propyl in front, or move this here, and then they've got the wrong names. Down here, The structure works, prop makes sense, cyclo makes sense, but they have the wrong ending. This isn't an ene, there's no double bond. So that's wrong. Okay. Down below is just a diagram, not a full question, but I thought I could run through how to name that as sort of a further example. So my strategy for naming these again is to sort of snake out the parent or the stem and then box out my alkyl groups or other functional groups coming off. So if I sort of start snaking out the longest chain, I go here, and then I could go down one or up one, so it's a tie. It doesn't matter which way I go. So that leaves a hydroxyl here, a hydroxyl there, and a methyl there. I like to star what side I have to count from. So we have to think of the family first. So we don't look at this methyl group, that'll be a branch. This is an alcohol, and the shortest way to get to our hydroxyls is from the right. So let's start building this name. We've got 1, 2, 3, 4, 5, 6 carbons. So this is hex. We've got 2 hydroxyls. So we have to put in numbers for both of the positions. And then because there's 2 of them, we're going to put di. And then because it's an alcohol, the OL for that family. So this is our first carbon, our second, our third, our fourth, our fifth, and our sixth. And then we have to keep this numbering system. So these hydroxyls are in the 2 and the 3 positions. Even if these numbers were the same, we still need both numbers and we still need the diol, unless there's only one possibility of numbering. And we've got our methyl group to deal with last, and it's way out in the 5 position. So 5-methyl, no spaces. It takes a little practice to line this up. Okay. Again, there is no space right there. Kind of another isomer type question. C6H12 is now what we have. So which of the following rows identifies a structural diagram and a UPAC name? So pretty similar type of question. This is another CnH2n. So 12 is double 6. So again, we're after ene or cycloanes. So we have to figure out which one of these makes sense. First thing that jumps out is we've got an ine here. We've got a triple bond. So there's no way this is going to work. This would be a 2n-2 type pattern. So now we've got to sort of go through A, B, and C. So our first one, there's a 5-membered ring plus another carbon is 6. So this is a C6. If we count the H's, there'd be 2 there, 2 there, 2 there, 2 there, and only 1 here because there's 3 lines coming out. So only room for 1 more bond, and carbons always have 4 bonds. So 2, 4, 6, 2, 4, 6, 8, 9, 10, 11, 12. So this works. And is this the right name? Methyl, yeah, we don't need a number. Cyclo, that works. And 5 carbons pentane. So the very first one was the correct answer. In the next example, we've got a cycloene. So that's going to fit down into that category. So it's not a 2n. It's a 2n-2. So there's not enough hydrogen. There's only going to be 10 here. C, let's figure what's wrong with this one. So we've got 1, 2, 3, 4, 5, 6 carbons. So that looks good. It is an ene. So it's going to fit there. I'm not going to count out all the H's, but it does work. I'm just saving a bit of time. It's the name that's wrong. We have to minimize the numbering to the double bonds. So we have to count from this side. So this is our first bond, that's our second bond. If we go this way, 1, 2, 3. So this should be a 2. Okay, The 3 is fine. It's the first, the second, the third carbon. Okay? So my red numbering for bonds is not the same as the carbon count number. You have to number twice, once for the bonds, once for the carbons. So that's what's wrong with those other examples. Now we're into an HMA type of question. Definitely one you want to read the answers first before you try to deal with all of this data. The one thing I will highlight, though, is there's kind of two distinctive parts. We have bromine on the end, so sort of one connection, bromine going 2 ways, and a bromine with carbons going all 3 ways. There's kind of a different sort of separation here. And same type of thing with our hydroxyl group in these alcohols. At the end, with carbons going 2 ways and carbons going 3 ways. So that seems to be repeating. So boiling point decreases, anyway, after which is a valid statement. So essentially which of these are true. So boiling point decreases. So boiling points are going down with more branching. So let's see, we go from sort of 1 branch off to 2, right to left, to 3. And if we look, the boiling points are decreasing. With our alcohols, we go 1 to 2 to 3 branches off, and we see the same decreasing trend. So A is looking okay. Let's look at the others. Boiling point increases as the length of the parent chain decreases. So if we have a smaller chain, the boiling point's going up. Here we have a chain of 4 carbons, then 3, and then 3 again. So that's not really a nice manipulated variable, and the boiling point is not going up. If anything, the trend is down. So this one is just definitely wrong. C, boiling point decreases as the number of carbons increase. That carbon count is actually a controlled variable. All of these have 4 carbons. So this one is totally wrong. Okay? Carbon's a controlled variable, not a manipulated variable. Last, boiling point increases as a functional group becomes less polar. That's not what's going on here. We have the same sort of addition. Okay? The polarity here is not changing. Okay? Particularly if we look at this subset to this subset, these all have hydroxyl groups. So that's not our manipulated variable. So polarity is not the change. So A is sort of the only one that works. This is the valid interpretation for the data above. Okay? But this is a much trickier question than the other ones we've gone through. So this is a continuation from the previous one. So this data goes with 25, 26, and question number 10. 25 I've put into the reaction section, so it'll come up later. So using the solubility data, so we're going to have to keep flipping back and looking at this column. Okay, so using the solubility data from the previous page, arranged organic compounds numbered above, in terms of decreasing solubility. So it is most soluble first going to least. If we just look, we can't answer this question. We've got to figure out what's going on because we've got different alcohols, not 4 carbons. We've got at the end, like we had before, we've got sort of 2 branches, right to left, and then we've got 3. Okay, so what's going on there? And then we've got this different compound from the top subset. So if we look at our alcohols, soluble, more soluble, most. So the most soluble is when we have tons of branching away from that hydroxyl group. Okay? Now it's not curriculum, but this would be called a tertiary alcohol, a secondary, and a primary. Something your teacher may or may not have gone through and not something they had to. So this COH has one thing coming off of it, 1 carbon. This COH has 2, right and left, and this COH has right, left, and up, the tertiary. Okay, so we've got to apply that, and then if we look at the solubility with the bromines, they're all insoluble. So this, no matter what, our 1 bromine example in 10 will be the least. So we have to start with the most. So that would be what has the most branches. So that's 3. Then second most would be 1. The straight one, there's just one sort of long branch. And then last, these are going to be insoluble. So you're not using knowledge that you've learned from your teacher. This is, can you take some data and interpret it? So these are the type of outcomes that aren't specific to organic. You should be able to interpret data within Chem 30 from any unit. Another question, sort of in the not memorizing, applying the knowledge that you have. So you have a compound you've never seen before. You know it's C10H16. So you can think of generic formulas. This is definitely not an ane. We don't have to think too hard because we're told it's an ene, okay, with a number of double bonds. Okay, so we'll have to think of that part later. When it reacts with excess hydrogen, we get a isomer. Okay. So which of the following is not an isomer of this compound? So we've got to figure which one is not, some number of double bonds, okay? Or the other option, so we can have an ene sort of times 1, 2, 3 double bonds, or the other thing that can kind of work is a cycloane, has the same type of pattern, or a cycloane that has a double bond that turns it into a cycloene. Any of these will sort of fit under that pattern. So A, B, C all sort of fit possible unsaturations, removing a couple H's. A, B, D. C is the one, this is a aromatic compound. This benzene is a C6H6, and then 2 of the H's come off to put in the side groups, but very different pattern. This is the one that doesn't have any possibility of being an isomer of the C10H16. You could just straight up count them all here. There is 10 carbons, but there's an H there, there, and there. None here, and there's just nowhere near 16 H's in total with the branch. So this is just a comment for benzene. What's the number of carbon-carbon bonds? This is where generic formulas can help. So if this was an ane, it'd be C10H2N plus 2. So it'd be 22. It's not an ane. There's only 16. So every time we take away a pair of H's, that would allow a double bond to be formed. So when we go down to 20, that'd be 1 double bond. Down to 18, that'd allow 2 double bonds. Down to 16, that'd be 3. And how do I know they're double bonds? Well, we're told it's an alkene. Alkene. So 3 unsaturations, so there must be 3 double bonds in that compound. Okay. So the top one, again, 27, you could just go through and count all the C's and H's, and that would let you know whether it was a C10H16. This one really required an understanding of going from saturated to unsaturated and how many pairs have been removed again. I guess you could think of this as 22 minus 16. So the ane down to what we have would leave 6 H's removed. They are removed in pairs. So another way to come up with the 3. A couple questions on this slide. So use the following information to answer question 25 on the top, and then number 9 a little further down below. So let's read the question, ignore the box. Which of the following rows identifies the total number of carbon-carbon covalent bonds in classification? So we need to know what compound are we talking about, and all we need from this box is butane. So C4H10, and we know butane would have to be a straight chain. So there's but just means, well, it means 4. It's right there. 1, 2, 3, 4. I'm not going to write in my H's. I'll put a little dashes where all the H's are, but that's not even needed. How many carbon-carbon bonds are there? 1, 2, 3. And maybe you've picked up by now, there's always one less carbon-carbon bond than the carbon count. So if you had a decane, there would be 9 carbon-carbon bonds. Okay. Then what's the classification? I really don't like this question. It's kind of a play on exactly what is classification, but this is unsaturated versus saturated. So again, not the type of question that I love, but that's what they've put in. Down to number 9. We've got a whole bunch of terms about butane that we have to sort through. A lot of these hopefully just come from memorization. I don't want to explain them all fully. All hydrocarbons are non-polar, so there's only C's and H's. Okay? The ane version, there was no mention of any branching, so it is straight chain. Okay? There's no 1-methyl or 2-methyl or anything like that. So what else? So we've eliminated that. Where does it fit in terms of boiling points? So with the anes, the less carbon it has, least amount of carbons or lower amount of carbons, less electrons, less London forces, and it'll have lower boiling points. So the eth is 2 carbons, prop is 3, and then we've got bute, which is 4. So it's highest in this sort of lineup they're laying out. So it's got the most carbons, so it would have the most London forces, most electrons, most London, highest boiling point of eth, prop, or bute. That's the heart of this question. So it would not be lower than ethane, it would be greater than propane. Okay. We've got an ane, so anes can undergo substitution. Yeah, addition, no. You need a double bond to do addition. You can burn any of these organic compounds, and you can do substitution with anes. UV light would be the main way to do that. So 2, 3, 6, 8 is the correct sequence. Okay. You're always going to get a fractional distillation question on Diploma, so hopefully these are well studied and something you will have a high degree of success. Fractional distillation is going to use boiling point physical properties. And in the tower, which I'm not going to fully draw and explain, but as you go up the tower, it's going to get cooler. And only the lowest boiling points are going to make it to the top before they condense. So the smallest will go to the top. The larger, higher boiling points will stay at the bottom. So the second part, the number of carbons in the molecules collected at the top of the tower will be less. So that makes this D. Another box, let's see what the question is first. Organic compounds that are isomers, so of the same C and H count of nonane are. So we've got an ane, this is a 2N plus 2. So we can't have any of these other types of families. They just don't have the same pattern. They won't be double plus 2. So this is 9 plus, doubled is 18 plus 2 is 20. So our first one, we've got the cyclo, and that's what makes this wrong. That is a cycloane. So it would have 2 less hydrogen than just a normal ane. So that doesn't work. And then we've got 2 more anes, but they're not cyclos. So these are both going to work. You could spend some time looking into the side groups, but it doesn't change anything. Those are just straight up anes. So 2 and 3 work. You missed that cyclo in there. That'd be easy to maybe miss, and you could easily think that it's all 3 just looking at the family. Another trickier question. This is really just analyzing data. So I don't want to spend a long time on this. It's not about studying content and knowledge. It's about data interpretation. So let's breeze through this. And it's a lot of just handling integers. And it's something I don't love about this question. You have to keep track of one negative numbers, what's bigger and what's smaller. So when you have a double bond compared to the ane, does the boiling point increase? And no, they actually go down from minus 90 to minus 100-ish when you go from the ane to the ene. And same here, you're actually getting colder when you go from the ane to the ene. So that one doesn't work. Again, you just have to handle the integers. A triple bond, does that increase the boiling point? So there we do have an increase in temperature. It's less negative. And here we have another less negative, an increase in temperature. So that works. Double bonds decrease the boiling point. Well, for the same reason that 1 is wrong, that is right. And that one's going to be wrong because we know 2 is right. It's just the opposite. Hydroxyl functional group increases the boiling point. You don't even have to think of any of the knowledge that your teacher gave you about hydroxyl groups or forces. Just look at the data. So when we go to the hydroxyl, the boiling point is increasing and the boiling point is increasing. And that's what that says. Same thing with our chloro. Don't use your prior knowledge. You can, but just use what's going on in your data. And again, we see a increase and we see a increase. So the 2, 3, 5, and 6 are right, and the other ones are incorrect. Again, don't overthink this by trying to use your knowledge. It's purely table interpretation. Back to something a little bit more straightforward, sort of more knowledge. Vitamin E is classified as blank, so what are our options? Don't think about it. Aromatic, aliphatic are the only two options, and we see one of those benzene rings that makes this aromatic. And contains what functional group? Don't think of them all. We only have two options, ester or hydroxyl. So I do see a hydroxyl right away there. And then if we keep looking, we do have an O here, but this O goes to 2 carbons, which is a ether, not covered in this course. Something I like to mention just so you're aware that it's not one of the things we've learned about. So there is no ester linkages in here, just hydroxyl. So it's aromatic and hydroxyl B. So we've got 3 pieces here. So these you really need to slow down, relax, and just go one piece at a time. Let's again go to the question before we jump up. Propane can be recovered from the organic material numbered. So how could we get propane? Well, this is really hopefully focusing you down here. And a key part of the Alberta oil industry is you take crude oil and you do fractional distillation and separate it out. So that's really what's being tested here. So it's crude oil that you're going to get propane from, and there's our fractional distillation. Now we've got something else going on. Propane reacts with chlorine in the presence of UV light. So as soon as you see UV, I'm thinking substitution reactions, and that's what you would have from an ane. Okay. And we've only got elimination and substitution, so that's going to be reaction, so that's 8. And then finally to produce hydrogen chloride gas and the organic numbered. So we're back to sort of some earlier numbers. So propane reacts with chlorine. Okay, we got the reaction to produce hydrogen chloride and what? So we've got propane. I'm not going to put in the H's. Just to speed this up, we're adding it, reacting with chlorine, UV light, and then what are we going to get? So substitution is only going to add 1 chlorine, either in the first position or the second position. So 1 chloro or 2 chloro are the 2 possible answers. when we look up at our possibilities, 1 and 2 are the only compounds we can see. But option 2 is a ene, and you do not make enes from substitution. So this isn't the only answer, but it's the only one we're given. That's our only possibility. So that's all the questions about sort of families. We did have a little bit of reactions mixed in here. I'm going to just super quickly, roughly categorize our reactions, and then we'll go through those questions. So addition, these are with our enes and our ynes. We need a double or triple bond. Okay. These work because the second bond or the third are much weaker. It's not within this course, but the first bond is called a sigma bond, very strong. The second carbon-carbon is a pi, or the third is a pi. Okay. And these we can break and add something to. Elimination reactions, this is when we make a double bond back. So it's kind of the opposite, and there's a couple ways to do that. So you can have alcohols or organic halides to make a double bond. Substitution we kind of just looked at. The big category I put these in is it's anes plus something, most commonly with UV light and switching. There's another type of substitution, but this is the main type that you see. So from families, we've got enes or ynes here. Here we see alcohols or organic halides. I'm just not writing the organic part. So all different families, addition, elimination, substitution. Esterification, these jump out because this is when we have an alcohol, OL, plus a carboxylic acid. So we have two hydrocarbon derivatives reacting. So that should jump out at you. Then a couple more options. We've got combustion, which you should have known about for years. This is when O2 is one of the other reactants. And then polymerization, we got two types. Addition, these we only have carbon in the backbone when we make our polymer. And in condensation polymers, there's going to be some oxygen in the repeating pattern. So that's the big difference. I know this is a super fast review, but trying to just sort of categorize things. And these categories can help you answer most of these questions. And university organic chemistry is way more complicated. You need to know the steps and the why that things happen. Here, again, categories work. So again, category-wise, enes, ynes, addition, anes do substitution. If you have an alcohol, it could be elimination or it could be esterification, depending on what it's with. And combustion and polymerization are just quite unique. So these are the outcomes you might see around reactions. So we'll look at less questions than we did before. So match the equations for the formation of greenhouse gases with the reaction types. We don't really care about the greenhouse gas piece. We just need to match what are these. So we have hydrocarbon combustion. So we're looking for oxygen as a reactant. That only shows up once. Substitution reaction. So this we're looking for an ane. And so let's see, we do have an ane there. We have an ane here, but we've already used that one. Here we don't have an ane. So here I skip when you're not 100% sure. Inorganic, so what doesn't have any carbon? And number 2 just sort of screams there. That's the only possibility with no carbon. And what's our addition? So where do we have an ene or an yne? And that's number 4. Okay. So the only thing left is the first one is our substitution reaction. It looks weird. It's not the typical type of substitution, but again, don't get stuck, particularly with slight nuances with substitution. This isn't the most common, but the other ones you could get without any doubt, and then you've just got the missing ones to do. It's really important you don't get hung up on these numeric response if one of the blanks you're unsure of. You only have to know 3 of the 4 most of the time. Sometimes you've got 8 and 12 options, and then you do need to think a little more. We've got an ester. It's worth reading the box because there's not much here with a line structure. The ester represented by the line was formed by what reactants? So anytime we have lines, I always like to put little circles at the line segments to just pop out that carbon count. The side without the C double bond O, which is this side, came from the alcohol. The side with the C double bond O came from the acid, and it can be on the right or left. And I'm kind of splitting things down the middle through that O. So the alcohol had 1, 2, 3 carbons in it. So that's a possibility. There's 3 again. Here, there's just no alcohol at all, so that doesn't work. And here, more than 3, I'm not even going to count, so that's not going to work. Let's look at the acid piece. We've got 1, 2, 3, 4, 5. So we need to have 5. This almost looks like an acid, but it's not. It's missing the hydroxyl group. Here we've got all we need for the carboxylic acid. 1, 2, 3, 4, 5. That works. So that one is B. Compound 2, which I grabbed from, didn't grab all the compounds from the given information. So there's our compound. Can be formed with what in what reaction? So how can we make this? So compound 2 is formed. So we were given the product. So how can we add this? And we're told we've got a double bond. So double bonds category-wise, substitution is when we have anes, addition, enes, or ynes. We've got to be addition with this ene. And what are we going to add? So there had to be a double bond, and we're just adding 1 Br. So we need 1 Br in our inorganic part. So there's the 1 Br option. This would give us a 1,2 or 1,3 dibromo. So that's not going to work. We've got another reaction. So pentanol is heated in the presence of sulfuric acid. We've got a chemistry. Let's see some chemistry. Let's see what the question is. In the reaction represented above, the type of reaction pentane 3-ol is undergoing is. So what's going on here? So we have an alcohol and it's turning into a double bond. So that's one of those previously mentioned sort of cookie cutter categories. That is our elimination. An alcohol to make a double bond. So we've got elimination, and why do you add something up here, or what do you put up here? You put catalysts up there to speed up the rate of reaction. And so this is not an equilibrium. That arrow is more distracting than anything. So it's really just testing knowledge of catalysts in the second part. Ethyl propanoate, so that's an ester. O8 is an ester, can be formed by the reaction of. So pretty straightforward knowledge here. The first piece came from the alcohol, the second piece from the acid. So we need a 2-carbon alcohol. So there's a 2-carbon alcohol. There it is again. That's a 3-carbon alcohol, and we need 3 carbons in the acid. That is 3 carbons, but it's not an acid. There's our acid, D. So do you know the order of the names in esters? Pretty much every diploma is going to have bromine reacting with double bonds or not reacting when there's an absence of double bonds. We have aqueous bromine is added, absence of light. So this is saying there's no UV, there's no substitution. Okay. So the acid, these are both acids that would react with bromine rapidly to become colorless. So what has a double bond? And only this one has a double bond. Okay. There's no carbon-carbon double bonds. Okay, this double bond is not going to react. We're studying the carbon-carbon double bonds, and that's what makes something unsaturated. So there's our double bond, and what's this last part? Rapidly to become colorless is blank acid. We did that because the acid is classified as, well, if it's an ene, it is unsaturated. If it was saturated, it'd be an ane and would not react. So the correct answer is D. Very common question, the bromine test. Definitely something you want to know, and it's reviewed in the previous video going through the outcomes of this course. Finally, our first polymer question. Again, we got two big types of polymers. One's where there's O in the backbone, which is condensation, and when it's all carbon, it is addition, polymerization. So we do have an O in the chain, okay, sort of on both sides. So this sort of screams condensation. I know I haven't read the question, but that's just needs to jump right out at you. The polymerization reaction above is, okay, I dealt with that, and the inorganic, so non-carbon-based product. Okay, in condensation reactions, you always get water coming out. You're moving OH and an H, and they come together to make water. So really more of a memorize than understand type question. You don't have to decode what's going on here. You should just know water is part of the condensation reaction. And that's it for the questions from the 2019 and 2017 released items. Hopefully going through these helps you with some strategies to tackle questions and not just learning knowledge. If you haven't looked at the first video on all the outcomes of the course, I encourage you to take a look at that diploma prep video. If you do like these, please consider liking and subscribing, and feel free to send me comments or even questions you maybe want me to try to answer. And over time, there will be a diploma prep video series about the outcomes and released item solutions for all 4 units in Chemistry 30.